Hello friends, today we are going to see how we can understand Zener Diode as the voltage regulator in just 10 minutes. Yes, in just 10 minutes. Let me tell you, in this video only we are going to see all the insights that are required to solve voltage regulator based sums. So before going to the Zener Diode as a regulator, we must know some basic concepts of Zener Diode. So let's see that one by one. So the first thing that we should know is that what is the basic difference between PN diode and Zener diode. I know you know that if PN junction is in forward bias, then you are going to replace it by a short circuit when it is ideal. If it is not ideal, then you are going to replace it by a voltage source with a forward resistance, right? And if it is in reverse bias, then you are going to replace it by open circuit, right? Well, for Zener diode, in the case of forward bias, it is same as of PN junction diode, but in the reverse biased, instead of the open circuit, it is replaced by a voltage source. Yes, due to this property, only Zener diode is used as a voltage regulator in reverse biased. Okay, so let's see the VI characteristics also. So you can see the forward characteristics of Zener diode, it is same as of PN junction diode. Okay, that is what we have seen here. For forward bias, it is same. But in the reverse bias, PN junction is act as an open circuit. It means that it will not allow any current in reverse bias. That's why it is also said that it is unidirectional device. While Zener diode, it is called as bidirectional device because it will allow reverse current. The doping of Zener diode is adjusted in such a way that it can handle that avalanche current also by maintaining this breakdown voltage, and this breakdown voltage is also called as Zener voltage. Okay, so you can see this is the VI characteristics of Zener diode. Only difference is in this reverse bias. You can see a PN diode cannot handle reverse current, but Zener diode can handle, and the voltage at which the Zener breakdowns, it is called as breakdown voltage as well as Zener voltage. Okay, so this was only the basic things that we should know is before starting the voltage regulator. Now we can start with the voltage regulator. Now we are going to see how we can check whether the Zener diode is in breakdown or not. So you can see this circuit is a basic Zener diode based regulator circuit. Here you have your Zener diode. This is a load resistor. This one is an input resistor, and here you have given your input. Okay, so the concept that we know is that for breakdown, V in must be greater than Vz. But let me tell you, this is a wrong concept, or you can say it is a partially right concept. This concept will be right only if RL is very much greater than Rin. Why? Because if RL is very much greater than Rin, then most of the voltage drop will be occurred across RL, right? So there will be only small voltage across Rin. So you can see Rin will act as a short circuit. More specifically, it will act nearly short circuit. Okay, so at that time only this condition will be valid. But now you may be thinking that what concept should we follow? So the concept that we should follow is that for breakdown we should check VO. If VO is greater than VZ, then we will say the Zener is in breakdown. If it is not, then our Zener will not be in breakdown. So let's see the proof of this also. For that, let us consider that V in is a small positive voltage, and you can say Zener is not breakdown yet. So now you can calculate VO from voltage divider rule. So you will get VO as RL upon Rin plus RL into V in. Okay, so this is what I have written here. Also, you can rewrite this equation in terms of V in, that V in will be equals to Rin plus RL upon RL into VO. You have just shifted this term here and you got this equation. Let me clear you once again why we are saying that for breakdown of Zener diode, VO must be greater than Vz. We know that for this Zener diode to be in breakdown, the voltage across this Zener diode should be greater than its breakdown voltage, right? So you can see the voltage across this Zener diode is nothing but the output voltage. Okay, so that's why we will say if VO is greater than Vz, then only our Zener is going to be breakdown. Okay, so this is what I have written here. If VO is greater than Vz, then only Zener will get breakdown. You can rewrite it as like this also. You can replace VO with this term, and if you shift this term towards Vz, you are going to get this equation. So what I'm saying is you can write it as VO as greater than Vz. Okay, and you can replace this VO with this term, so you will get RL upon Rin plus RL into V in greater than Vz. Okay, now if we shift this term towards Vz, we will get V in is greater than Rin plus RL upon RL into Vz. Okay, so this is what I have written here. Okay, so you can use both the equation, either this or this, you will get the same thing. Okay, still if you don't understand by this concept. So let's take V in as 15 volt, Vz as 10 volt, Rin as 1k and RL as 1k. What we know that for breakdown of Zener, voltage across Zener diode must be greater than Vz. Okay, so it is nothing but Vo must be greater than Vz, and here you have calculated Vo for small positive voltage when Zener is not breakdown. It is RL upon Rin plus RL into V. Now if you put all these values, you will get 1 upon 1 plus 1 into V. It is nothing but Vo is 1 by 2 into V. Okay, so if V in is 10 volt, then you will get Vo as 5 volt. If it is 20 volt, then you will get Vo as 10 volt. And we want that Vo must be greater than Vz. So we can say if and only if V in is greater than 20 volt, then only our Zener voltage is going to break down. Here you can see we have a V in is equals to 15 volt. If it is less than 20 volts, so we can say our Zener diode won't be breakdown. You can also verify this by this equation also. We know that for breakdown, V in should be greater than RL plus Rin upon RL into Vz. If you put all the values, you will get 1 plus 1 upon 1 into Vz. It is nothing but V in is greater than 2 Vz. So this becomes our condition for breakdown. So you can see 2 Vz nothing but 20 volt. So if and only if V in is greater than 20 volt, then only our Zener is going to break down. Here you can see V in is 15 volt, which is less than 20 volt. So you can say our Zener won't be breakdown for this case. If let's say V in is equals to 22 volt, then you can say our Zener is going to break down. Now let's see the actual Zener regulator operation. Regulation is divided into line regulation and load regulation. In line regulation, line varies. It means that input voltage varies and RL is fixed. While in case of load regulation, load varies. That means RL varies while V in is fixed. Now you may be thinking, why am I varying only these two parameters although I have a 4 parameters? As you can see in this equation, for breakdown, V in must be greater than RL plus Rin upon RL into Vz, right? But the thing you should take note of it that Vz is always fixed, right? Once the Zener diode is manufactured, Vz will be always fixed. Also input resistance is going to be fixed, right? Only the load resistance as well as the input that we are going to provide will be varying. Okay, so that's why we consider only this two parameter instead of all these 4 parameters. Okay, now let's start with the line regulation. In line regulation, line varies, RL is fixed, and the circuit for line regulation is this one where you can see input is varying, RL is fixed. Okay, if you get a arrow on some source or a element, it means that source or a element is of varying one. So you can see we have a arrow, so we can say V in is varying. RL doesn't have arrow, so RL will be fixed. Okay, so this is a circuit that we must follow for line regulation. In question, if you get this type of circuit, then you can directly say it will be of line regulation. Okay, so while solving question, it will be very much helpful. So now we get to know that for line regulation, line should be varying and RL should be fixed. So if RL is fixed, so we can say IL should be fixed. Why? Because IL is nothing but VO by RL. So if RL is fixed, so IL must be fixed. Now let's come to the I in input current. Input current is nothing but V in minus Vz upon R in. Okay, so this is what I have written here. Now we know since it's a line regulation, so V in will be vary. So we can say input current will also vary. Since this two term is fixed, only this V in is varying, so IN will be also vary. So from this equation, we get to know that I in is in varying condition. Also from KCL, you can get to know that I in is nothing but Iz plus IL. Okay, so this is what I have written. Since you know that IL is fixed and I in is variable, so Iz must be variable, right, to maintain this equation. This is what I have written here. Since I in is variable and IL is fixed, so Iz must be variable. Okay, so take note of this also. Now coming to this important parameters, this is the important because in the exam you are directly asked about this parameters only. What is I in maximum, what is I in minimum, what is IZ maximum, what is IZ minimum, okay, from the given circuit. Okay, so I in maximum will be Iz max plus IL. Why? Because only I in and Iz vary. Okay, so for I in maximum, Iz should be maximum, and for I in minimum, Iz should be minimum. Okay, so this is what the two condition that you should take note of it. Okay, now let's see for load regulation. Load regulation, it means RL will be variable and input voltage will be fixed, and the circuit corresponding to that is this one. V in is fixed and only the RL is variable. The arrow says that the element is variable. Okay, so since here you can see RL is variable, so IL will be variable. Why? Because IL is nothing but VO by RL. So if RL is variable, so IL is going to be vary. Now coming to this I in is nothing but V in minus Vz upon R in, okay. But here we have a V in as fixed one, Vz and R in is already fixed, so we can say I in will be also fixed. So from this equation we get to know that I in is going to be fixed one in case of load regulation. Now from KCL we get to know that I in is nothing but Iz plus IL, okay. So this is what I have written here. But since IL is variable and we know that I in is fixed, okay, so to maintain this condition Iz must be variable, okay. So we can say that if IL is maximum, Iz must be minimum so that I in is fixed, and if IL is minimum then Iz should be maximum such that I in is fixed, okay. So this is what I have written here. If IL is maximum, Iz must be minimum such that we can get I in as fixed one. If IL is minimum, then Iz should be maximum to maintain I in as fixed condition. And if you want the relation between IL and RL, we know that IL is equals to VO by RL. So if IL is maximum, then RL should be minimum. If IL is minimum, then RL should be maximum. Why? Because it is inversely proportional, right? So take note of these two conditions, okay. This is very much helpful to solve the gate sum. Now the thing that we should note is that in no load condition, it means that RL is infinity, there is no load connected, then IL is going to be 0. Why? Because IL is nothing but VO by RL, okay. So if it is infinity, that it means 1 upon infinity is nothing but 0, so you will get IL as 0. So in that condition In will be equals to Iz, okay. So if this is 0, it means that In will be equals to Iz only. Okay, now let's see some useful power dissipation formula from which the direct question has been asked. We know that power dissipation in any element is nothing but voltage across that element multiplied by current flowing through that element, okay. So for Zener it will be Pz equals to Vz into Iz. Vz is voltage across Zener diode and Iz is a current flowing through that Zener diode, okay. And the unit for power is watt, right? This is what we all know. Now if I say what will be the formula for maximum power dissipation, it means the power dissipated should be maximum. Since we know that Zener voltage is always fixed, so for maximum Zener current should be maximum. Why? Because Zener current is variable but Zener voltage is not variable, okay? So to gain power as maximum, Iz should be maximum, okay. Similarly for minimum power dissipation, Iz should be minimum, okay. So this is the two important formulas which we should take note of it. Now coming to the power rating, from this also question has been asked. The first thing what we should note is what is power rating. Power rating is nothing but maximum power dissipation that can be handled by Zener diode. Okay, so we can say power rating is nothing but Pz max, and Pz max is nothing but Vz into Iz max. Okay, Vz is fixed, only Iz can be variable. Okay, so to get Pz max, Iz should be maximum, okay. Now in some question you get a term like minimum power rating, okay. So for this what we should take care is that minimum power rating is nothing but maximum power dissipation. Why? Because it is asking for minimum power rating and we know that power rating is nothing but maximum power dissipation. So minimum power rating will be maximum power dissipation that can be handled by Zener diode, okay. So for minimum power rating formula also we are going to use Pz max formula only, that will be Vz into Iz maximum, okay. So if I sum up whole video, first we have seen what is Zener diode, what is the difference between Zener and PN diode, then we have seen a VI characteristics of Zener diode, then we have seen how we can identify if Zener diode is in breakdown or not, then we have seen the two types of regulation, then we have seen a important power dissipation. Hello friends, today we are going to see the trick to solve Zener diode based voltage regulator sums. So let's jump direct to the sum and there only we will see the trick. So the first sum is from EC 2002, a Zener diode regulator in the figure to be designed to meet the specification IL 10 milliampere, VO is equals to 10 volt and V in varies from 30 volt to 50 volt. The Zener diode has Vz equals to 10 volt and IZK, basically knee current, is 1 milliampere given. For satisfactory operation, what will be the correct condition? Let me tell you, I am assuming that you know basic concept of Zener diode based voltage regulator. If you don't know, you can watch my previous video that was fully dedicated to only the concept of Zener diode based voltage regulator. You can find the link of that video in the I button, okay. So let's start the solution. Basically the trick to solve this type of question is you have to narrow things as much as possible. So you can see here, we are given with this V in varies from 30 volt to 50 volt. It means that V in is varying. So we can say it is a line regulation question. Okay, line regulation question. So we will say if V in varies, so I in is also going to be vary. Why? Because we know I in formula is V in minus Vz upon R. Basically from here V in minus Vz upon R. Okay. So if V in varies, I in is also going to vary. Okay. And if we apply KCL at this node, we will get I in is equals to Iz plus IL. Right? This is your I in is equals to Iz plus IL, right? Okay, this is what I have explained you in brief in the previous video. Okay, so it will be better if you watch that video first and then move to this video. Okay, so here I in is varying, IL is fixed. Okay, here we know I in is varying and IL is fixed. Why IL is fixed? Because IL is nothing but VO by RL. Okay, so IL is fixed here, but I in is varying. Okay, so to maintain this equation, Iz should vary. Okay, so we can write it as I in maximum will be when Iz is maximum, right? IL is always fixed, and when I in is minimum, then we will say at that time Iz should be minimum, right? And IL will be fixed. This is our first sum. That's why I'm explaining this. In further sum, we are not going to write these things. So here you can see we know IZK. IZK is nothing but minimum Zener current. Okay, so we know IZ mean here. So we are going to use this equation, right? We can't use this equation because we don't know IZ max, right? And I in minimum will be when V in is minimum. So it will be V in minimum minus Vz upon R. Okay, so this will be V in minimum is 30 volt. Okay, 30 minus Vz is nothing but 10 volt. 30 minus 10, R is we have to find out, right? So this is our I in minimum. We know Iz minimum. IL is simply 10 milliampere. So if we put all this thing into this equation, we will get 30 minus 10 is nothing but 20 by R is equals to Iz minimum is 1 milliampere plus IL is 10 milliampere. Okay, so we have 11 milliampere here. So our R will be 20 by 11 into 10 raised to minus 3. So we can write it as 20 by 11k. 20 by 11 it means 1.90k, 1.8k. So we will get 1.8k here. So R is our 1.8k. Okay, so we got to know that here we are getting 1800 value. Why? Because 1.8k is nothing but 1800 ohm. Okay, so we got the value 1800, but we have to find out this relation also. So for that, here you can see we have I in minimum. Okay, and you can see I is inversely proportional to R, right? So if I in is minimum, then R should be maximum. So from this equation we can say this R is nothing but R maximum. So we will write it as R should be less than equals to 1800 ohm for the satisfactory operation of this voltage regulator circuit. And if you try to find out this R with this 50 volt as your V in, you will get R less than 1800. You can cross check it and let me know your answer in the comment box. Now let's see this sum. This is of EC 2004. In the voltage regulator shown in the figure, the load current can vary from 100 milliampere to 500 milliampere. So from this equation itself, you can say that it is a load regulation problem, right? Because this RL is varying, that's why this IL is varying, right? Assume that the Zener diode is ideal, Zener knee current is negligibly small, and Zener resistance is 0 in the breakdown region. The value of R is, so basically we have to find out this value with the condition that Zener resistance is 0 and Zener knee current is also negligibly small. It means Zener knee current is 0 itself. We will use the same trick, that is narrow the things as much as you can. So here from this line you get to know it is a load regulation problem. Okay, load regulation problem. It means here IL is varying, IL varying. And from this side of this circuit you can see I in will be fixed. Why? Because V in is fixed here, so we can say I in is fixed. And from KCL we know that I in is nothing but Iz plus IL. Here we know that IL is varying but I in is fixed. Okay, so to maintain this equation Iz should vary. So we can say when IL is at maximum value, Iz should be at minimum value, right? To maintain I in at fixed value. Similarly for IL minimum, Iz should be at maximum. Okay, such that we will get the same I in. Now the thing is, which equation should be used? Here you can see we know the Zener knee current. It means we know the Zener minimum current. Okay, so we are going to use this equation, right? Here we have Iz minimum and IL max. We know IL max, right? IL max is nothing but 500 milliampere, and we have to find out this I in. So I in will be 12 minus 5 upon R, right? R we don't know, R we have to find out. So if we put this into this equation, we will get I in as 12 minus 5 upon R is equals to Iz minimum is 0 milliampere. Why? Because here you can see Zener knee current is negligibly small, so we can consider it as 0 milliampere plus IL max. IL maximum is 500 milliampere. Okay, so this is a 500 milliampere. So our R will be 12 minus 5 is nothing but 7 upon 500 K, right? It is nothing but 7 upon 500 into 1000. So 1, 2, so we will get the resistance value as 14 ohm. So from the option you can see the correct option is this D option. So you can clearly say if you try to narrow down the things which you are given in the question, you will get to the answer very quickly and without any mistake. Okay. Now onwards I'm not going to write the equation again and again. We will directly use the trick. So let's see this third question. This is of EC 2013. IZK is equals to 10 milliampere given. It means that minimum Zener current is given. To maintain 5 volt across RL, okay, the minimum value of RL in ohm and the maximum power rating of the Zener diode in millivolt respectively are. So basically we have to find out RL minimum and minimum power rating. Okay, you can see in this question this part is fixed. It means here only the load is varying, so it is the question of load regulation. Okay, so we get to know it is a question of load regulation. It means that IL is going to vary, okay, and I in will be fixed, and to maintain this thing IZ is also going to vary, right? This is what we have seen in the previous question also. Now the question is which equation should we follow? So here you can see we have IZK. Basically we have IZ minimum here, so we are going to use the first equation where we were having IZ minimum and IL maximum. So we are going to use that equation. I in is equals to IZ minimum plus IL maximum. And you can see in the question itself we have to find out the minimum value of RL. As you know that IL is inversely proportional to 1 upon RL. If we are finding the IL maximum value, in turns we are getting the RL minimum value, right? So from this equation only we will get RL minimum directly. So if we put the things into this equation, we will get I in is nothing but 10 minus VZ. VZ is nothing but 5 upon 100 equals to IZ minimum. IZ minimum is here 10 milliampere plus IL maximum. We don't know IL maximum, so we will keep as it is IL maximum. This is in milliampere. Okay, so this will be 5 upon 100. It is nothing but 50 milliampere, right? So we will get 50 milliampere. Here we have a 10 milliampere plus IL maximum. So IL maximum here we will get as 40 milliampere, right? This is our IL maximum. So our L minimum will be this 5 upon 40 milliampere. Okay, it will be in K. So 5 upon 40 is nothing but 1 upon 8 K. 1 upon 8 is nothing but 0.125 K. So we will get 125 ohm. So from the option you can see we neglected this two option since we get RL as 125 ohm. So our answer will be from this two option only. So now let's find out this minimum power rating of the Zener diode. Here we want a minimum power rating. Okay, so minimum power rating is nothing but maximum power dissipation. This is what I have elaborated in my previous video also, so it is better to watch that video also. Minimum power rating is nothing but PZ max. PZ max will be VZ into IZ max. Okay, so here you can see we have to find out IZ max now to find out this PZ max. So now the question comes, what will be the IZ maximum? We know the equation as I in is equals to IZ maximum when IL minimum. Okay, so if we use this equation, from this equation we can get this IZ maximum. But again the question comes, what will be the IL minimum? IL will be minimum only when RL is maximum and value of load resistance can be infinity. So at that time IL minimum will be 0 milliampere. So if we put all this thing into this equation, we will get I in is nothing but 50 milliampere. IZ max we have to find out, and this IL minimum is 0 milliampere. So we can get IZ max as 50 milliampere. Okay, this is what we got. Now we are going to put this value into this equation. So we will get PZ max equals to VZ. VZ is nothing but 5 into IZ max. IZ max is nothing but 50 milliampere. So it will be ampere into volt is equals to watt. Okay, so 5 is a 25 to 50 milliwatt is your answer. Okay, so you can see from the option this B is the correct answer. So you can see here, if you narrow the things as much as possible, you can solve this type of question very easily without any mistake and quickly. Now let's say this is a tricky question. In the circuit shown below, the Zener diode is ideal and the Zener voltage is 6 volt. The output voltage VO in volts is. Until now we have find out the R value, we had find out the current value, we had found out the minimum power value, but here the question is I have to find out the output voltage. Okay, and let me tell you, this is the question of EC 2013, and the question is we have to find out this VO. Okay, so the first thing to solve this type of question is we have to check whether the Zener is getting breakdown or not. This is also I have explained you in my previous video. You can go there if you want the proper concept. Okay, so the first thing that we have to check whether this Zener is in breakdown or not. So for that we will open this Zener diode and we are going to find out the voltage across this Zener diode. So for that we are going to use voltage divider rule. So from voltage divider rule we will get VO as 1 upon 1 plus 1 is nothing but 1 by 2 into V in is 10. So from this equation we get VO as 5 volt. You can see this 5 volt is less than 6 volt. Okay, so it means our Zener is not breakdown yet. So whatever the voltage present across this resistor will be our final voltage. Okay, so our correct answer will be this 5 volt. Okay, so take note of this type of question also, because in this type of question your chances of making mistakes is higher. Okay, now let's see this question. This is of EC 2018. IZ minimum is given. The input voltage Vi may vary by 5% from its nominal value of 6 volts. So from this sentence only we can get to know that V in is varying here, so it means it is a question of line regulation. The resistance of the diode in the breakdown region is negligible. Okay, the value of R and the minimum required power dissipation rating of the diode. Okay, so basically we have to find out the value of R and the minimum power rating. Okay, so if we try to solve, we know that it is a line regulation problem. It means that I in is going to vary, I in is varying, I L is fixed, so for that IZ should be vary, right? So now the question comes, which equation should we follow? Should we follow I in minimum or should we follow I in maximum? So for that you have to check for what value of Zener current you know. So you can see here we have IZ minimum, so we are going to use the first equation in which we have I in minimum. So I in minimum equation is IZ minimum plus IL. Okay, for I in maximum it will be just IZ maximum. Okay, I in minimum will be when V in is minimum. For V in minimum we should know the minimum value of voltage. So here we have 6 volt plus minus 5%. Okay, 5% of 6 volt will be 10% is 0.6, so 5% will be 0.3. Okay, so it will be 5.7 to 6.3 volt. Okay, so the minimum voltage is 5.7 volt here, so we can write it as 5.7 minus 5 upon R, right? Pi minus Vz upon R equals to IZ minimum. IZ minimum is 2 milliampere here. IL will be 5 upon 1K. It is nothing but 5 milliampere. So this is 7 milliampere. So R we will get 5.7 minus 5 is nothing but 0.7 upon 7 K, as this milliampere will go upside and it will convert into this kilo ohm. Okay, so we will get 1 by 10. It is nothing but 0.1 K. So the answer will be 100 ohm. Okay, so we get to know that either B or C will be the correct option. Now we have to find out the minimum required power dissipation rating. Okay, so don't confuse between this minimum power dissipation and minimum power dissipation rating. Okay, we know that minimum power dissipation is nothing but Vz into Iz minimum. Okay, but minimum power rating is maximum power dissipation, that is Pz maximum. It is nothing but Vz into Iz max. Here you have to note the last word. Here we want that minimum power dissipation rating. It means that here we have to find out minimum power rating. Okay, so we are going to follow this one. Okay, so we have to use that Pz max wala formula. Pz max is nothing but Vz into Iz max. So here we have to find out Iz max first. Okay, so for Iz max we will use the equation this one. I in maximum is nothing but Iz maximum plus IL. Okay, so for that we want I in maximum. So I in maximum will be when Vi is maximum. Vi maximum is 6.3 volt. Sorry, here it will be 6.3. Okay, so we will get 6.3 minus 5 upon R. We know this is 100 ohm. We can write it as 0.1 such that this will be in milliampere. We want Iz max. IL we know it is 5 milliampere. 6.3 minus 5, it will be 6.3 minus 5 upon 0.1. 6.3 minus 5 is 1.3. 1.3 upon 0.1 is nothing but 13 milliampere is here. So we will write it as like this: Iz max plus 5 milliampere. So we will get Iz maximum as
13 minus 5, it is nothing but 8 milliampere. Okay, now we are going to use the PZ max wala formula. It is nothing but VZ into IZ max, right? VZ is nothing but 5 volt, 5 multiplied by 8 milliampere. This is in volts, so we will get 5 8s of 40 milliwatt. Okay, so you can see the correct option will be this B. So you can see if you try to narrow the things as much as possible, you will get to your answer very quickly, very easily, and without doing any mistake. Okay, so that's it for today. Thank you guys.